Now we're going to start bringing everything all together. So we've done momentum and we've done energy, but let's talk in terms of conservation of momentum and energy and decide when those two things are conserved or when one or the other isn't. So let's think in terms of an elastic collision. Now remember, an elastic collision would be like if I have a ball going this away and a ball going this away, and they hit each other, they bounce off, they don't stick. So in this case, this is a perfectly elastic collision, meaning that after the collision, then I'd have one of the balls going back that way and one of the balls going back that way. So we can write that in terms of momentum as being, let's see if we call that mass 1 and that mass 2, that let's define directions, shall we? I'm going to say that that way is positive. That mass 1, velocity 1, going in the positive direction, minus mass 2, velocity 2, because remember these are vector quantities, it's going back that way, equals, now mass 1 is going in the negative direction, so just for convenience, I'm going to start with mass 2. So mass 2, v2 prime, minus mass 1, v1 prime. That's the conservation of momentum that we've been working with. The only thing I've done differently here is I've gone ahead and defined what directions these things are going right out of the gate. So instead of doing the sum of the two momentum on the left equals the sum of the two momentum on the right, I've just enforced the direction for the velocity vectors. So that's the momentum conserved. And let's see what we have. We have motion. So as far as energy goes, we have kinetic energy. So if I were to write this in terms of kinetic energy, I would have, let's see, let me do a different color. I'd have 1/2, oops, that's not going to show. 1/2 m1 v1 squared, so the kinetic energy from this, plus 1/2 m2 v2 squared. Now notice I added these two quantities together. I didn't subtract them. These are not vector quantities. Another way to think about that is even if this was a vector quantity, its velocity, which is the vector quantity, is being squared, so the negative sign would go away anyhow. But these are scalar quantities, not vectors. So it's going to equal what happens in the end. So I have 1/2 m1 v1 prime squared. Ooh, starts getting a little messy. Plus 1/2 m2 v2 prime squared. What I'm going to do in the next video is show you how we can relate all of these quantities together. But the first thing you'll notice is if I don't have these in terms of energy, something that's going to make the math a little easier for me is all these 1/2s would cancel out. So if you're not given something in terms of joules and you just know something about initial or final velocities, then you could start off writing your energy equations without the 1/2s because they'll cancel. But at any rate, so if I have an elastic collision, both momentum and energy are conserved. And a way to think about that is I'm bouncing off. Where would the energy go? So if I don't have an external force acting on the system, taking any energy out, so no work done, then this stays the same. If I don't have an external force acting on the system, then the momentum stays the same. But what happens in an inelastic collision? So in an inelastic collision, let's see, what have we done? We've done things like cars hitting each other. So something like a car going this way and a car going this way. Then they hit and stick, so I end up with like this overall car thing moving off, probably in like that kind of ish direction, depending on their masses and velocities. So I have, this is my initial going to my end. Well, we've seen with this inelastic collision, let's see, we know that I end up with m1 v1 plus m2 v2, and I'm writing it this way for a reason, equals the sum of the masses Oh, I'm gonna run out of space, times v prime. Now, what's not consistent here is I drew a circumstance that is in 2 dimensions. So I have motion in the x and motion in the y. So this thing here I'd have to break up into x and y momentums. I wouldn't be able to just do this. But the general case for momentum in an inelastic, so they're sticking collision, is that the momentum that I have before goes into the momentum I have in the end. So let's think about what happens here when these 2 things stick. So if I have 2 things sticking, well, we'll make a car part. So I'm going to go to just a one-dimensional thing. So this guy's going, has some sort of V initial, and this one is stopped. And then in the end, what happens? I have like this whole mass 1 plus mass 2 thing. Well, for this to happen, I'm not bouncing off. What do I have? I mean, think in terms of if you've ever had that sickening feeling of hitting a pole or something, scratching the car, right? You feel that in the car, and the translational effect is you get out and you see a dent in your car. So if I am deforming something, if I am changing its shape, that takes energy. So momentum is conserved. Momentum is conserved. Conserved, if I can spell that. Energy is not. I have some sort of non-conservative force or energy in there. In this case, if I have 2 cars colliding, then I have energy being lost to heat, being lost to changing the actual shape of the system, which more often than not translates into some sort of heat or thermal transfer. So energy is not conserved. I can't just write it as this initial kinetic energy, whoops, sorry, will equal this final kinetic energy, but momentum is. So in our next example, then, we'll talk about some of these and how we can apply conservation of energy and momentum when we have things that are more complex mathematically.